Section: Introduction. In this section, we introduce multimodal generative models that can understand and create various types of content, such as text, images, videos, and audio. These models enhance AI systems by allowing us to gather information from different sources, learn from diverse data, and respond flexibly to user requests by generating the necessary content dynamically. While we have a clear choice of model architecture, transformers, the best generative objective is still uncertain. Typically, current multimodal models are trained together using a method that approximates maximum likelihood over sequences of images, text, and other types of data. Autoregressive models, for instance, break down continuous data into quantized forms and optimize likelihood through a series of conditions, generating content in a fixed order. They perform well in generating text and images but are slow and inefficient when generating image tokens due to the high correlation between nearby tokens, leading to unnecessary computations. Additionally, these models are hard to control and struggle with tasks like inpainting unless specifically trained for them. On the other hand, continuous diffusion models work effectively with continuous data like images. They add Gaussian noise to data and are trained to remove this noise, maximizing a lower likelihood bound. However, they are much slower to train with text data compared to autoregressive models. Since text is discrete, adding continuous noise to text tokens doesn't create meaningful changes. This raises the question of how to create a unified generative approach for text, images, and other modalities. To tackle this, we present UniDisc, a unified multimodal model that uses discrete diffusion. Instead of using continuous Gaussian noise, UniDisc corrupts data by randomly masking tokens and learns to convert these masked tokens into multimodal tokens during inference. We explore how discrete diffusion through masking can be applied to both text and images with a unified set of parameters. Our architecture tokenizes both text and images together and employs full self-attention to map masked sequences to clean sequences by sampling from a combined vocabulary. We evaluate UniDisc on various multimodal generation tasks and compare it to autoregressive models. Our findings show that UniDisc achieves better scores in quality and diversity, demonstrating strong joint inpainting capabilities that previous models could not achieve. We also find that UniDisc is more efficient in generating content, producing higher quality outputs within the same computational budget. Furthermore, it shows improved performance in retrieval tasks due to its flexible sampling steps. Finally, we scale UniDisc to a large model with 1.4 billion parameters, trained on extensive image-text datasets, and make our code, model weights, and datasets publicly available for further exploration. Section Summary. In this section, we discuss the development of UniDisc, a unified multimodal model that utilizes discrete diffusion to effectively generate and understand text and images by masking tokens, addressing the inefficiencies of autoregressive models. We highlight UniDisc's superior performance in terms of quality, inference efficiency, and joint inpainting capabilities compared to traditional models, while also noting its scalability and public availability of resources. Section: Discrete diffusion models. In this section, we discuss discrete diffusion models, which have become a promising alternative to continuous diffusion for handling discrete data types. We note that the first discrete diffusion model was introduced for binary variables and later expanded to include categorical variables, proving effective in generating images. D3PM further developed discrete diffusion by introducing a broader range of noising processes, allowing for more adaptable noise schedules. Recent advancements, such as those by SEDD, introduced a new loss function called score entropy, which connects continuous and discrete spaces. Additionally, recent studies have shown that discrete diffusion can achieve text perplexity levels comparable to GPT-2. We also highlight that while these methods show potential, they primarily focus on language modeling tasks. Our work aims to broaden the application of discrete diffusion across various modalities, demonstrating its effectiveness within a unified architecture. We observe that unified models for processing multiple modalities have made significant progress, with examples like Flamingo, LLAVA, and Chameleon. Specifically, Uni D3 explored discrete diffusion for images and text but treated each modality separately, using different operations for each. We explain that diffusion models are generative models that learn to create data distributions by reversing a process that adds noise to clean data. This process starts with a clean data sample and gradually introduces noise until it resembles pure noise. The forward diffusion process involves a series of transitions, where each state at a given time is sampled from a Gaussian distribution. In contrast, discrete diffusion models adapt these principles to discrete structures, using categorical distributions for transitions instead of Gaussian ones. The forward process for discrete models is characterized by a cumulative transition matrix that dictates the probabilities of moving between discrete states. D3PM generalizes this framework with various transition matrices, with our work using an absorbing transition matrix, which has shown the best performance for both text and images. This matrix includes a special absorbing state represented by a mask token. During the forward transition, the probability of an input token remaining the same is defined, while the probability of it being masked is also specified. We note that the objective function for optimizing the model is similar to that of continuous diffusion, but it uses a Bernoulli distribution instead of a Gaussian one. Finally, we simplify the objective function by focusing on masked tokens, leading to a re-weighted masked generative modeling loss. We also compare different design choices in our work, noting variations in noising schedules used in language models versus image generative models. Section Summary. In this section, we discuss the evolution and application of discrete diffusion models, which adapt continuous diffusion concepts for discrete data types, particularly in image and text generation. Our work extends these models to multiple modalities within a unified architecture, demonstrating their effectiveness across various tasks while building on recent advancements in discrete diffusion techniques. Section: Unified Training via UniDisk. In this section, we describe our approach to unified training using UniDisk. We train a bidirectional transformer that employs two-dimensional rope embeddings for image tokens and one-dimensional rope embeddings for text tokens, while also incorporating learned embeddings specific to each modality. This setup gives our model the flexibility to adjust resolution during inference and allows us to optimize computation by primarily training at a lower resolution. We utilize the same objective function as previously defined, but for us, the input consists of both image and text tokens. We implement classifier-free guidance, CFG, to balance the quality and diversity of our generated outputs. Specifically, we randomly mask tokens from one modality with a probability of 0.1, enabling UniDisk to learn the unconditional likelihood for both image and text. During inference, we apply CFG for conditional generation, whether converting images to text or vice versa, to manage the trade-off between quality and diversity. Our empirical findings indicate that decoding images requires significantly fewer sampling steps compared to text. We observe that the Frechet inception distance, FID, stabilizes within 32 sampling steps for images, while text generative perplexity takes around 400 steps to stabilize. This discrepancy poses a challenge for unified modeling, as the maximum number of sampling steps is limited by the slower modality. To address this, we propose caching the tokens of the faster modality, which is the image in this case. However, our current training scheme does not allow text tokens to interact with image tokens from previous denoising steps. To overcome this, we suggest using different time schedules for each modality, a slower schedule for text and a faster one for images. We define minimum and maximum time steps for inference and establish a ratio indicating how much faster image inference is compared to text inference, which we find to be approximately 10. During training, we randomly sample text time steps and adjust image time steps by offsetting them with a specific delta, ensuring that image time steps do not exceed a certain limit behind text time steps. This modality-specific scheduling allows for efficient KV caching of image tokens during inference, leading to quicker inference times. To enhance training stability, we implement query key normalization and use RMS norm for other normalization processes. We also apply sandwich normalization around each feed-forward network to better control activations in deeper layers. Additionally, we analyze the noising schedule and find that a linear schedule can overly weight early time steps, hindering convergence speed. We adopt a strategy to limit the minimum weighting to a specific value to improve this. Next, we discuss unified sampling with UniDisc. In our masked discrete diffusion, we map masked tokens to visible tokens through a series of denoising time steps. We explore various sampling strategies and find that the confidence-based sampling from mask GIT performs best for our unified modeling. We enhance this approach by incorporating modality-specific caching and nucleus sampling on the logits. By caching image token keys and values at regular intervals, we achieve lower latency, especially with longer sequences or larger batch sizes. Our complete algorithm and implementation details are available for reference. Section Summary. In this section, we describe our approach to unified training and sampling using UniDisc, which employs modality-specific embeddings and different time schedules for image and text tokens to enhance inference speed and training stability. We also explore various sampling strategies, finding that confidence-based sampling from mask GIT, combined with modality-specific caching, significantly improves performance in masked discrete diffusion tasks. Section: Experiments. In this section, we compare UniDisc with an autoregressive AR baseline across different tasks, metrics, and datasets. We maintain the same architecture, hyperparameters, and data, differing only in the attention mask and loss functions. Our AR baseline uses a standard language model from Chameleon, which is a decoder-only transformer with causal attention and rotary positional embeddings. To implement classifier-free guidance, we apply a dropout of 10% to modalities during training. For UniDisc, we drop out both modalities, while for the AR baseline, we only drop the first modality in the input sequence. Our experiments aim to address several questions. How does UniDisc perform compared to AR models in generating image-text pairs, both unconditionally and conditionally? How effective is classifier-free guidance for AR models and UniDisc in conditional generation? How does UniDisc's training efficiency vary with different ratios of image-text tokens? How do different sampling strategies for UniDisc impact its generation results and inference speed? How does UniDisc perform in image-language reasoning tasks compared to AR models? What design choices in UniDisc enhance its performance? Finally, we demonstrate that we can scale UniDisc to a model with 1.4 billion parameters, trained on 500 billion tokens, and we qualitatively evaluate its capabilities. For our datasets, we use various training and validation sets, including DataComp1B, CC12M, CLEVR Math, and CLEVR Ref. Our evaluation datasets consist of a held-out validation set from DataComp1B and CC12M, along with Flickr, MS Coco 30K, and Winnoground. In evaluating multimodal generation, we assess both UniDisc and AR models in unconditional and conditional tasks. We use three common evaluation metrics: joint perplexity, which measures how well a model fits different validation sets; Frechet inception distance, FID, which assesses the quality and diversity of image generation; and clip score, which evaluates image-text coherence. While we lack a direct equivalent to FID for text, we use clip score to measure coherence by conditioning our model on an input image. We present results for conditional image-text generation, where we condition on an image to generate a language description and vice versa. For unconditional results, we refer to the appendix. Our findings show that UniDisc significantly outperforms AR in conditional generation while performing comparably in unconditional generation. We attribute this performance gap to classifier-free guidance. Without CFG, the results for both models are similar, but increasing CFG benefits UniDisc more. The iterative generation process of diffusion allows for blending conditional and unconditional predictions, while AR models generate data sequentially, making it harder to mix in unconditional predictions. In joint image-text inpainting, we demonstrate that UniDisk can perform this task without fine-tuning, a capability not found in popular generative models, which are typically autoregressive or mixed models. We also fine-tune an AR model for joint inpainting, but UniDisk still shows superior performance without any adjustments. Regarding training efficiency and inference speed, we analyze the compute efficiency of generative models. Previous studies have shown a power law relationship between compute cost and distribution fitting for AR models. However, there has been limited research on the training efficiency of discrete diffusion models. We conduct an analysis comparing UniDisk and our AR baseline, finding that UniDisk requires approximately 13.2 times longer training to achieve the same loss as AR models. While training efficiency is crucial, inference efficiency is equally important for deploying these models at scale. We compare the inference efficiency of UniDisk and our AR baseline, measuring joint generative perplexity, image FID, and text perplexity. Although AR may appear to perform better based on some metrics, we find that UniDisk has higher entropy at a given perplexity. We emphasize that evaluating generative quality should consider both generative perplexity and entropy together, as low perplexity can sometimes result from repeating the same tokens, a common issue with AR models. We illustrate these degenerate cases in the appendix. Section Summary. In this section, we compare UniDisk with an autoregressive baseline across various tasks and datasets, focusing on their performance in multimodal generation, training efficiency, and inference speed. Our findings indicate that UniDisk significantly outperforms the autoregressive model in conditional generation due to the benefits of classifier-free guidance, while also demonstrating superior capabilities in joint image text inpainting without fine-tuning. Section: Multimodal Discriminative Performance. In this section, we explore the discriminative performance of generative models, which have shown to be effective in recent studies. We assess the discriminative abilities of AR models and UniDisk through cross-model retrieval tasks involving images and text. Our evaluation uses the Winogrand dataset and a separate Datacomp 1B validation set, training on 18 million text-image pairs. To enhance text retrieval for the AR model, we adjust the order of modalities during training, placing the image first 20% of the time, which we found beneficial. We report the accuracy of image retrieval, text retrieval, and joint retrieval for both AR and UniDisk models. In image retrieval, we provide a text caption with 16 images, where only one image is correctly matched. We determine accuracy by checking if the correct image has the highest probability given the text. The same method applies to text retrieval, where we check the probability of the text given the image. For joint retrieval, we look for the correct pair among random combinations, verifying if it has the highest joint probability. Our findings indicate that UniDisk significantly outperforms the AR model across all tasks. To delve deeper, we analyze joint retrieval accuracy across different denoising steps and CFG values, discovering that these factors greatly influence UniDisk's performance. Unlike the AR model, which has a fixed number of denoising steps, UniDisk can utilize many more. Next, we demonstrate that UniDisk scales effectively with parameters and dataset size. We trained a model with 1.4 billion parameters using web-scale data in two stages: a low-resolution pre-training phase with 250 million image caption pairs at 256 by 256 resolution, followed by a high-resolution fine-tuning phase. Our dataset includes 200 million open web images, recaptioned for better quality, along with smaller datasets like PixelPros and JourneyDB. We also created a custom dataset of 18 million synthetic images, emphasizing the importance of image caption alignment. In both training stages, we address dataset imbalance by sampling more from higher quality sources. We fine-tune our model at 512 by 512 resolution using 30 million image caption pairs. Due to space constraints, we also examine various architectural and objective design choices on a smaller model. We present the training curve for our 1.4 billion parameter model and compare UniDisk to other multimodal models on standard benchmarks. Our qualitative results showcase capabilities like zero-shot text-conditioned image inpainting, standard text-to-image, and image-to-text generation. Additionally, we illustrate image editing capabilities, showing that UniDisk can enhance text-image pairs through a process of noising and denoising without specialized fine-tuning. Finally, we analyze UniDisk's joint generation, revealing that it produces images uniformly across concepts rather than by area.